First, an overview of the DATV-Express hardware for those of you that have not already seen it. First, we have the power input, which can be between about 8 and 15 volts. Then we have the power regulators for all the onboard chips, the USB 2 interface and its associated crystal, and the USB 2 controller, the FPGA, the D2A converter, the anti-alias filters, the VCO and IQ modulator, the amplifier, the socket, the LED and PTT lines, a parallel interface for selecting bands, unused A to D converter, unused flash. This is the main screen of the DATV-Express program. I'll come to what the individual items are in a moment. First, I'd like to go through the menus. Firstly, we have the file menu. You can open a configuration file, save a configuration file, save the current configuration as a different file name, restart. This reloads the FPGA code on the DATV-Express board, resets the codecs, and also resets the capture device, and exit to exit the program. The current file name configuration that you're using is displayed on the top bar of the program. Next, we'll go to the capture menu. It has video capture. Here you can select the device that you're capturing from and the format that you're capturing with. You can change that. So for example, if we select this device and then click on here, we get the formats available on the device. The interlaced feature does not work. If we select OK, it will update the parameters. If we select cancel, it will cancel our choice. We will cancel. As well as the video, you can select the audio source. In this case, we're capturing from the vMix audio, but there are a number of other devices available on my machine. The codec menu. You can select the video codec. You have a choice of MPEG-2, MPEG-4 or HEVC. You can also select the group of pictures and the B-frames. The video bitrate twiddle is primarily used for reduced bandwidth television. At very low bit rates, the software does not correctly choose the correct bit rate, so you can modify it using this parameter. With the audio codecs, at the moment you only have a choice of MPEG-1 layer 2, and I have only allowed 2 bit rates, the very lowest being 64K bits and the normal 192K bits. 64K bits is good for audio, but if you have any other input like music or other noises, you get a lot of artifacts. The enable audio button allows you to disable or enable the audio. This is primarily for reduced bandwidth television, where you may not wish to use the bandwidth you have available to you to encode audio. You may wish to use it all for video. Next, we come to the SI table settings. These are the conventional settings that allows the receiver to know the identity of your picture, your channel name, your call sign, and what a current event is, and some text describing the event. Next, we come to the options menu. The options menu is a general purpose menu where I stick anything that I don't know where else to stick it. In this case, the only entry is on-air format. The on-air format gives the format that will actually be transmitted over the air and can be different to the captured format. You have the width and height and also the number of frames per second. If you select input format, this selects the same format for the transmitted signal as the capture device. This is normally the best choice. The aspect ratio sets the aspect ratio of the picture. The FFmpeg itself will actually use the format that you've specified to try and figure out which of the aspect ratios to use. You can override it, but the results might not always be spectacular. Next we come to the modulator menu. This basically configures the DATV-Express itself. You have a common entry. This is for parameters which are common to all transmitted formats. In this case it's the transmit frequency, the symbol rate and the transmitted level. The transmitted level can go from 0 to 47 in 1 dB steps. This matches the attenuator inside the modulator chip on the DATV-Express board. You can select which transmit mode you want, DVB-S or DVB-S2. DVB-S2 being the latest addition to the program. The DVB-S encoding is done actually in the FPGA, so the overhead is very low and can be used on small computers. DVB-S2, because of the size of the transmitted frames, has to be done inside the PC. The Express board does not have enough memory to cope with it. The PTT port option allows you to configure a 4-bit parallel port on the side of the DATV-Express card, and this can be used for controlling antenna changeover relays, band select, etc. There is PTT sequencing, so that you can have a separate PTT for the transmitter and a separate one for the preamp, so that you don't put a lot of RF up before you switch the preamp out. The apply button on this menu allows you to apply these parameters without having to save or to restart the program. Now we come to the actual modulation modes. First we'll look at DVB-S. Under this menu you can only select the FEC mode. This is standard. Next we come to DVB-S2. The DVB-S2 is a lot more sophisticated. You can select the constellation, whether it be QPSK, 8PSK, 16 APSK or 32 APSK. The filter, transmitted filter roll-off. The smaller the number, the more rapid the roll-off, but the more signal to noise that you will need because the eye pattern closes. The FEC rate that's permitted, and the pilot symbols. The modulation format actually determines the available FEC format. So for example, if I select 8PSK, you'll find that these FEC formats are no longer allowed. Again, with say 32 APSK, even fewer formats are allowed. So if we go back to QPSK, you'll find that the selection actually has been deselected, so you be careful to select it again before doing an OK. Pilot symbols. Pilot symbols adds extra information into the transmitted waveform. These symbols are used primarily in the receiver for training an adaptive equalizer. The pilot symbols make it much easier for the receiver to cope with bad signals. The adaptive equalizer in the receiver uses the symbols as known symbols to train its equalizer. That causes an update of the filters coefficients in the adaptive equalizer. If you do not have pilot symbols, it has to do the equalization blindly. In other words, it receives a symbol, it doesn't know what it is, it makes a decision as to what it is, and it feeds that information back into the equalizer to update the coefficients. Therefore it trains on a blind signal. If pilots are selected, these are known symbols, and the equalizer has got 100% certainty of knowing that the information it's being fed into it is correct. So that covers all the menu items except for the obligatory help. This basically tells you what version of the software you're running, and it includes the information as to where to get the source, which is a requirement of the GPL license, because I'm obviously using the FFmpeg codecs here, and we like to conform to the requirements. Next, finally, we come to the screen, the final screen. TS record records the transport stream when transmitting. This is recorded to disk. Carrier only transmits a continuous wave carrier at the same power level as the modulated signal. Video ident puts a simple overlay of your call sign on the transmitted picture and can be used for identification purposes. These figures here correspond to the configuration and gives you an overview of how you've got your system set up. The TX level shows the transmitter level in dBs above something. The TXQ shows the number of outstanding packets waiting to be transmitted from the PC to the express card. The TX level, which is the latest feature I've added, allows you to set the transmitter level from the front panel. The level only comes into operation when you release the button, because I2C messages have to be sent across the USB link to the modulator chip itself. Finally, we come to the most important button, the push to transmit, the push to televise. Call it what you may. When you press this button, the display annunciator goes from standby to transmit and changes colour, as we shall see. There we go. We're now transmitting. Here you can see the transmit queue is flickering. This is perfectly acceptable. If, however, the transmit queue begins to monotonically increase, it indicates that the PC has lost communication with the DATV-Express board, and this is not a good situation to be in. You will probably have to restart the entire program. You can try doing a restart, but I suggest you exit and restart the program. This concludes the overview of the DATV-Express software. DVB-S2 QPSK modulation. DVB-S2 8PSK constellation. DVB-S2 16 APSK modulation with a 0.2 roll-off. DVB-S2 32 APSK with a 0.25 roll-off. This is DVB-S2 with a 0.35 roll-off. This is also the roll-off used by DVB-S. If I now go to a 0.2 roll-off, now you can see a narrowing of the signal. 0.25 is a intermediate between the two, which I won't bother with. But the change probably won't make much difference to us, but certainly on a wideband satellite link it would make a considerable difference. Back to 0.35. Watch now. There you go. That's it. Currently with DVB-S2 I haven't added all the required interpolators and filtering for the reduced bandwidth modes, so the picture above shows you why you shouldn't operate the software below 2 megasymbols at the moment. I'll do a comparison with DATV-BS software, which does actually have the correct filtering, so stand by. And this is with the DATV-BS software operating at 1 megasymbol per second. There's a 50 meg sweep across the spectrum analyzer, so you should always have filtering after your the output of the DATV-Express. Although the side alias products are fairly low down, it's definitely worthwhile having filtering in there. This is what the DATV-BS spectrum looks like when operating at 125 kilosymbols per second. Finally, I thought I'd give you one last shot with everything turned up full. This is DATV-BS2 32 APS-K 9/10 FEC. Transmitted bitrate is 53.4 megabits per second. CPU usage 42% on my PC. As you'll notice, the spectrum is losing some of its shape, and that's due to the hardware filters on the DATV-Express board. They're actually plus minus 5 meg filters, roll off 3 dB points I should say. But you can demodulate this signal with a sat-link receiver. But that's about it. It won't go any further. The Express FPGA can, but it's limited by the filters on the hardware. DATV-Express is now reaching the end of its life, so we've now got to look at alternatives. It's because of the small quantities we manufacture in, the board's very expensive, so there are better options available either now or in the near future. What we're looking at, or what I'm looking at, is replacing the Express board with something like the Lime SDR, which will be available at the end of the year. It's cheaper than the Express board. It has an extended frequency coverage from 100 kilohertz to 3.8 gigahertz. They're also developing another board which will extend that up to about 12 gigahertz, but I'm not sure when that'll be available. It has a lot of other nice features that the Express doesn't have. For example, receive as well as transmit channels, and two of them, and it also has anti-alias filters which are programmable within the chip itself, so we won't need to rely on fixed anti-alias filters like we do at the moment with the DATV-Express board. So a brief overview of the hardware itself. As you can see, it uses a bespoke chip from Lime Microsystems in the UK. It has a fairly large Altera FPGA on it. It's the same family of chips that is used on the Express board, but it's a much more powerful and much more modern one. So I'm familiar with the development tools on that. It has USB 3 support on it, so there's a much wider bandwidth between the SDR board and the host itself. And I think that's basically all the interesting features as far as the specs are concerned. So as well as obviously a direct replacement for Express, it should be possible to port the current Express software to work with this board fairly quickly. But until I get one of these boards, I won't know how long it's going to take. I have a personal project to implement a DVB-S2 ground station based on the Lime SDR, and that will include a receiver, so that should be fun to implement. I've got some of it done already and I understand most of it. I've also been looking at the S2X standard, which is an extension to the S2 standard, and it includes some very low noise signal to noise ratio VLSNR modes that have got a lot of FEC on them, and are supposedly should work down to about 10 dB below the noise floor. Whether that's true or not, we will find out. But I have to state that this is a personal project, and there's no time scale involved in it. Hopefully I'll have something up and running by next, when the SHILSAT is launched. And as a companion to the SDR, the Lime SDR, I'm thinking of using a single board ARM device, which I will describe in a moment. But that has the advantage, obviously, of being portable. It's not like dragging a PC about, and will make quite a good combination. Here's the proposed board that I'm going to use for receive. It's produced by NVIDIA, that do the graphics cards, and it has a number of advantages. It has USB 3 on it, which is one of the few ARM boards that do at the moment. It also has a 192 core GPU, which allows you to do operations in parallel. The DVB2S spec was designed to take advantage of the parallel processing abilities of ASICs, and was designed around that feature. Now, ASIC programming obviously is expensive and not possible for me to do in the lab, so another alternative would be FPGAs, but that's fairly time consuming to do this sort of stuff. So GPUs is a third alternative. They can be programmed in a language called CUDA, which is very similar to C, and it's basically an extension of C. So that should be fairly simple to do. If we look at the specs for the Jetson TK1, you'll see that it's got 192 CUDA cores. It's got a 4+1 ARM cores. In fact, there's 4 main ARM cores and a second ARM core, which is used for various other things. And they run at the 4 main cores run at up to 2.3 gigahertz. It has a USB 3 interface, as I've already mentioned, which means it's ideal to work with the Lime SDR. Got a fair amount of memory on it, 2 gig of memory. Runs Linux, of course. And it's got eMMC, which is a very fast version of Flash, and a number of other features, which makes it a good candidate for implementing modems and the like on. Right, we now come to the second possible alternative replacement for DATV-Express, and that is a standalone modulator stroke encoder board. The chips are being designed by a company in Taiwan, and they're more happy to work with us, even though we will have very small volumes. Their chip currently supports DVB-T, ATSC, some cable modem standards, and some of the digital television standards used in the Far East. Unofficially, the chip also supports DVBS, but they don't market it as a DVBS chip because it doesn't support the wide bandwidths that and high symbol rates that a satellite would require. But it looks as if it would be suitable for our use. Until we get hold of one of these boards, we won't know, of course. At the moment, we're just going backwards and forwards, querying things and getting an understanding of how the hardware works, what the chip will do. It supports MPEG-2 and H.264, MPEG-4, AVC. This now brings me to the end of my presentation. Thank you for your attention. There'll now be a short question and answer session.